Hi friends, Dr. Voroli is here. Welcome back. Today we are learning the moving iron instrument. Moving iron instruments are used for direct AC signal measurement. We have seen the PMMC instruments. Those are responding to DC voltage and DC currents only. Whereas for measurement of AC quantities, the moving iron instruments are developed. They can directly respond to AC signals. There is no need of rectifiers. There are two types of moving iron instruments. One is attraction type and second is repulsion type. Let us see the attraction type of moving iron instruments. The figure shows the construction and various parts of moving iron instrument. It consists of a coil. The coil is wound on a former, plastic former. In the air gap, there is a moving iron mechanical arrangement. It's a pivoted moving iron plates there and balancing and control weights. To this moving iron shown here by orange color plate, there is a pointer connected. And to the other side, there is a air damping cylinder. This air damping cylinder is used to control the damping torque so that sudden changes should not affect the motion of the pointer. And these instruments can be balanced or maintained to the zero position by balancing by gravity or by a spring to restore the zero position. New type of devices doesn't use the gravity balancing. They are using the spring balancing. The spring provides the control torque so that when no signal is applied, the instrument pointer should be at null position or zero position. The aluminum piston is used for producing the damping torque. Here you will see in a three-dimensional diagram, there is a coil wound on a former, plastic former, and in the air gap of the coil, there is a assembly of balancing weight and a moving vane. Moving vane is basically a oblong iron plate which is magnetic, which is of magnetic material, and the pointer is connected to this moving vane. Now, if you see the operation of this in the figure 2, it is shown when the current is flowing through the coil, it produces the magnetic field as shown by the force of magnetic lines. The pivoted piece that is called as moving vane, it is an iron piece. Due to this the magnetic field produced by the electric current, this iron piece experience a force of attraction and it is attracted inside. When it is attracted inside, the pointer connected to this pivot, which is also connected to the moving vane. When moving vane is moving inside, the pointer is moving on the scale. The direction of the pointer movement is shown in the figure. When this moving vane is attracted inside, the pointer is moving to the right side and the scale is connected below this pointer. So, the force produced is proportional to the current flowing through the coil, and the current flowing through the coil is proportional to the external applied current. and therefore the deflection pointer is proportional to the applied current. Here, the figure shows the operation slightly in detail. See, when the coil is unexcited, the position of the pointer is shown and the vane position is shown here. When the coil is energized, depending on the magnitude of the current, the electrical field, the magnetic field strength is set up in a air gap here. And due to that, there is force acting on this iron piece that is called as moving vane. And depending on the exerted force, the position of this moving vane will be decided. That in turn decides the deflection angle theta. Whereas in repulsive type of moving vane instrument, if you see the construction, again there is a coil. The coil is fed with the external current, whereas in this air gap, there are two vanes. One is a stationary vane that is connected to the field coil shown here, and another is connected to the pointer shaft. When the electric field is applied to the coil, it causes the field to be produced on the iron vanes. So top ends are getting north pole and bottom ends are getting south pole. And when no excitation is applied, for example, at that time these two plates are touching to each other. That time pointer will be on zero position. Whenever the current is applied, since due to magnetic field in the air gap, top ends of the vane is say north pole and south end of the bottom end of the plates become south pole, then two north pole and two south pole they repel each other, and due to this repulsive force the shaft is getting rotated. The amount of rotation decided by how much repulsive force is developed. This repulsive force is proportional to the applied current. More and more applied current, larger will be the repulsive force and larger will be the pointer displacement. The pointer displacement is proportional to applied current, and this way the current can be measured on the calibrated dial. The 3D view of this is shown in the figure here. You will see there is a coil, and inside the coil air gap there are two vanes. One is fixed vane and another is a moving vane. The spring here is a control spring. When no excitation is applied, these two vanes are touched to each other. When current flows, the repulsive force is developed between fixed vane A and moving vane B, and they repel each other, and repulsive force decides the deflection of the pointer. That deflection is shown here when the current is moving in the coil. And here below the pointer there is a calibrated dial shown. On this dial, the deflection can be directly scaled in terms of voltage or current. Okay. So, same thing is expressed by the mathematical relationship. When the excitation is applied to a coil, there is magnetomotive force developed, say M1 and M2. The repulsive force F is proportional to the product M1 into M2. Whereas M1 and M2 magnetomotive force is proportional to the magnetizing force H. The magnetizing force in turn is proportional to the current. So, since F is proportional to say m1 into m2, that is m square is proportional to h square, and since h is proportional to I, therefore the magnetizing force developed is proportional to I square, and therefore the deflecting torque produced is proportional to I square. The controlling torque produced by the spring is proportional to theta. So controlling torque proportional to theta. But at equilibrium, when the pointer stop moving at an angle theta produced by the deflecting torque, at that point the controlling torque is equal to deflecting torque. Comparing the equations of deflecting torque and controlling torque, theta is therefore proportional to square of the current. The dial of these instruments are marked directly in terms of quadratic scale, and therefore the dial will read the theta which is proportional to current. This way the AC moving iron instrument works. And that's all, folks. Here we end with unit number 4. Here some of the questions on unit 4 are given here, and short answer questions, those are asked in the examination, those are also given. So most of the questions answer is covered in the explanation of the instrument itself. You have to just review it and get ready for the preparation. Thank you. Thank you very much. Bye bye.